Hi everybody, I'm Gabriele Civitarese and I'm an assistant professor at the University of Milan in Italy. I'm a member of the Everywhere Lab, that is a research lab that is focused on data management for pervasive and mobile computing. Today, I will talk about our work that is about federated clustering for personalized sensor-based human activity recognition. Sensor-based human activity recognition, or HAR, is a very well-established research area due to its many applications ranging from healthcare to well-being. In the literature, the majority of approaches for sensor-based HAR are based on supervised deep learning. These methods allow reaching very high recognition rates, so they are very effective for this task. Nonetheless, HAR is still a hot topic today, because indeed, the deployment of real-world HAR systems is still limited by several open research problems, like label data scarcity, or continual learning, or personalization aspects. Ideally, the most effective solution to build reliable HAR models would be to collect for each user personal label data and build personalized models for each user. However, acquiring enough label data for each possible user in order to have reliable HAR models is not feasible because annotation is time-consuming, is costly, and is very intrusive. For this reason, in the last years, collaborative learning solutions emerged. In collaborative learning, the idea is to distribute the label data collection on a large number of users in order to build a single global HAR model that generalizes over many users. However, centralized approaches for collaborative learning have some challenges that needs to be tackled. First, there is privacy, because activity data is sensitive, as it may reveal personal habits or health conditions. Also, there are scalability problems, because collaborative learning means sharing a huge amount of raw sensor data and the labels to a server. So there are problems related to communication latency and computational costs. A possible solution that has been proposed in the literature recently is federated learning, and it has also been proposed for human activity recognition. The idea behind federated learning is that also the training process is distributed among the participating clients. So each client uses its available label data to train a local model. Then only the local model parameters and not the data are shared with the server. So each client transmits only some parameters like the weights of a neural network. Finally, the server aggregates the local model updates obtained from the clients in a privacy-preserving fashion in order to generate a single global HAR model. However, the application of federated learning in human activity recognition is limited by the non-IID problem. The global model ideally should generalize over a large number of users. But the problem is that each user may perform activity in a very personalized way. So different users perform activities in different ways. This is made due to different physical characteristics or different age or different habits. So activity data actually is non-IID, that means non-identically and independently distributed. And federated learning solutions are based on local optimization. So each client locally trains a local model, and this solution based on local optimization is not adequate for non-IID data. So there are several skewness that we can find in human activity recognition data. As I was mentioning before, there is the feature distribution skew, that is that each subject may perform an activity in a peculiar way. For example, the walking activity can be performed in a very different way if we are talking about a young subject or an elder one. Also, there is the label distribution skew. So in this case, different users may have different routines. For example, a sporty subject spends more time running than a sedentary one. So the sporty subject will have more labeled data about running with respect to the other subject. Another skew is the quantity distribution skew. So different subjects may have significantly different availability of label data. So a user may have collected more label data than another. In the literature, there are some solutions that have been proposed to tackle the non-IID problem in federated learning-based human activity recognition. The most common solution is based on transfer learning. And here the idea is that the global model built by the server in federated learning is then fine-tuned on each user with transfer learning approaches. However, the problem of this approach is that balancing the trade-off between generalization and personalization is challenging considering real-world scenarios. Another type of approach is multitask learning. So in this case, only the shared layers of the network are learned in a federated approach, while the personal layers of the neural network are learned locally. However, the major problem of multitask learning approaches is that they are mainly based on convex objective functions that limit scalability and complexity of HAR models. So in this work, we propose FedCLAR. And the idea behind FedCLAR is to mitigate the non-IID problem in federated learning-based human activity recognition. The idea of FedCLAR is that the local model updates are clustered on the server side of the federated learning with the objective of deriving groups of users that perform activities in a similar way. So the result of FedCLAR is that on the server side, we have a specialized model for each cluster of users. And the idea is that the data in each cluster actually minimizes the non-IID of data. Okay, so the users in the same cluster perform activities in a similar way, so they minimize, then each cluster minimizes the non-IID of data. This is a broad overview of how FedCLAR works. So we can see on the top that we have several models on the server side. For example, we see cluster 1 model. So as I was saying, we have a model for each cluster that we derive server side. And if we go in the bottom, in the client side, this model corresponds to the cluster 1 that is a specific cluster of clients that performs activities in a similar way. Okay, so we have the cluster 2 model that corresponds to a cluster 2. Okay, but if we go on the right, on the bottom, we see that there is a group of users that is called non-clustered users. As we will see later, not every user may actually necessarily belong to a specific cluster. So there are users that perform activities in some way that is different from the majority of the clusters. So in these special cases, actually, if we go up to the server side, these users do not have a specialized cluster-based model, but they use a general global model that is a classic global model in federated learning that is trained considering all the clients participating to federated learning. So in this case, non-clustered users use a generic global model. Finally, we can also observe on the client side that each client also uses transfer learning approaches to further personalize the model weights. So let's talk about how we compute similarity between users. In classic HAR, we can consider two users similar if they share similar sensor data patterns. So in this way, we are saying that they are performing activities with similar patterns. However, raw data is not available in federated learning settings because only the model weights are shared with the server. But our idea is that two local models with similar weights have been likely trained with similar sensor data. So if two local models are similar, it is likely that they have been trained with similar data, and so it is likely that the corresponding users perform activities in a similar way. So this is the idea behind this similarity. And FedCLAR in particular relies on cosine similarity that in the literature proved to be effective for this task. So it is a cosine similarity between two different model parameters from two different clients. However, we do not consider the whole parameters to perform this similarity, but only the ones that encode personalized information. For instance, consider a convolutional neural network. The layers that are closest to the output are the ones that encode subject-specific characteristics and features, while the layers that are closest to the input actually encode high-level features. So in this case, we can consider the last layers of the neural network as the personalized parameters of a model. Clearly, personalized parameters strictly depend on the model that is used for federated learning. Now, let's talk about how hierarchical clustering works in FedCLAR. So what happens is that we perform pairwise similarity to group local model updates. So it's a bottom-up strategy, and it is based on the similarity that we described just before. And it starts with one cluster for each user. So when two clusters are grouped based on similarity, a new specialized model is generated. And the two clusters are merged using FedAVG, that is the classic algorithm for aggregation in federated learning. And this process is repeated until convergence. So there is a threshold on the similarity. So when we do not find two clusters that are similar according to this threshold, the process terminates. And we only consider the clusters that have more than one user. And the singleton clusters are considered as non-clustered users. And as I was describing before, those users are not using specialized cluster models. Okay, in order to understand how hierarchical clustering is integrating in the whole federated training process, we need to take a step back and understand how federated learning process works in a standard setting. So what happens is that in classic federated learning, like FedAVG, the global model, that is a single one, is trained in several communication rounds. So let's see what each communication round is about. So the first step of a communication round is that each client trains the local model and then sends the resulting parameters to the server. Finally, the server aggregates these parameters and the clients, after this process, receive the updated global model. Communication rounds are repeated over and over until convergence. So it is not a single step, but it's a set of communication rounds that are repeated until convergence. What happens in FedCLAR is that this protocol is a little bit different in the server side. So from the client side, the protocol is the same. What is changing is from the server side. So let's see what happens on the server side of FedCLAR. So at the beginning, we have a certain number of communication rounds, in this case R-1, where only a single global model is trained, so there is no clustering. And the process is exactly the one that I described just before. However, at the RF communication round, hierarchical clustering is applied to obtain specialized model. So we wait a certain number of communication rounds in order to have reliable local model parameters that go through a certain number of communication rounds in order to perform reliable hierarchical clustering. If we do clustering at the very beginning, the quality of clusters is not good. During the remaining communication rounds, the server updates the specialized global model. So after the RF communication round, we do not have anymore a single global model, but we have a specialized model for each cluster that we derived with the hierarchical clustering. So let's describe how we evaluated our approach. Our experimental setup is very simple. So the activity model is just a feed-forward neural network trained on handcrafted feature vectors. So we choose a very simple approach here because our goal is to evaluate the impact of clustering. So we didn't want to choose a complex neural network, only a simple one to understand the impact of our clustering approach. Also, the advantage of this model is that it's very lightweight and is suitable for mobile devices. So how we divide the data set? So the 70% of each user data is used during the federated learning process to train the global models, so to derive cluster and cluster specialized models. The 30% of each user data is not used during federated learning, but is used later to evaluate the effectiveness of our solution. So 70% used for federated learning, 30% only used to evaluate the effectiveness, and this split is performed on each user. We consider two publicly available datasets. The first one is MobiAct, and the second one is Wisdom. MobiAct has 60 subjects, while Wisdom has 36 subjects. Both datasets, as devices, as sensing devices, have a smartphone in the pants pocket and are based on inertial sensors from the smartphone, like accelerometer. In MobiAct, activities are walking, jogging, jumping, going upstairs, downstairs, and sitting, while in Wisdom, the activities are walking, jogging, sitting, standing, and taking stairs. These are the main results of our evaluation. So we considered three different baselines. The blue bar is the classic FedAVG approach. So this is the classic federated learning algorithm that does not consider the non-IID problem. The orange bar is FedHealth, a recently proposed federated learning approach for activity recognition that only uses transfer learning to tackle the non-IID problem. The green line is our FedCLAR, but without the final transfer learning step that is performed locally, while the red bar is our final solution, that is FedCLAR. So as we can see, FedCLAR outperforms the other baselines, even considering FedCLAR without transfer learning. So clustering outperforms only using transfer learning to address the non-IID problem. However, if we also apply transfer learning after clustering, we can see that there is a further improvement in the recognition rate. And the results are the same for both datasets. In these plots, we show the trend of F1 score with respect to the communication rounds. So on the x-axis, we have the communication rounds. On the y-axis, we have the F1 score. And the red vertical line is the communication round where clustering occurs. And we can see that in both datasets, after the clustering round, the F1 score increases very rapidly with respect to the other solutions. So here we show that clustering is very effective in improving the recognition rate. So these plots show the results at the cluster-based level. So on the x-axis, we have the clusters that have been derived by our methods, by FedCLAR. And on the y-axis, we have the F1 score, and the different bars are the different baselines. And what we observed on both datasets is that cluster by cluster, FedCLAR outperforms the recognition rate with respect to the other approaches. And we see that on not clustered users, actually FedCLAR performs exactly as FedAVG and FedHealth, because here the not clustered users actually use the global model that is trained by all the participating clients. Okay, before concluding this talk, I would like to make a note about personal data protection, because initially at the start of this talk, I was mentioning that federated learning actually mitigates the privacy problem by sharing weights and not data. However, it is still possible to infer sensitive data from the weights of the federated learning global model. There are several attacks. One of these is the property inference attack. And the problem is that revealing private information of a subject actually may also imply revealing private information about the whole cluster. So suppose that an attacker finds out that a specific subject from the model weights has the Parkinson's disease. Well, all the other subjects that are participating in the same cluster maybe can have the same disease if they are grouped by similarity. Here we propose some possible solutions to address this problem. One of these possible solutions is using trusted execution environment, so secure hardware solutions to protect both the code execution and data inside secure hardware to run FedCLAR algorithms in a secure way. Another approach may be distance preserving homomorphic encryption. So in this case, the client can encrypt the local model weights before sending them to the server in a way that the server can still perform some computation without knowing the content of the weights. Finally, another possibility is to use local differential privacy to include noise in the local model updates. However, here the problem is to balance the trade-off between utility and privacy. Okay, let's conclude this talk. We talk about FedCLAR, that is a personalized federated learning approach to mitigate the non-IID problem. And FedCLAR shows promising results on 2 public datasets. Currently, we are planning several future work. One of these is clearly privacy-aware approaches to protect model weights, as I was saying before. But also an evaluation on a large scale is needed to truly assess the effectiveness of federated learning for HIR, because we only consider datasets that have at most 60 subjects, but federated learning should work for thousands and thousands or millions of subjects. Finally, we would like to tackle the labeled data scarcity problem by using self-supervised or semi-supervised learning approaches included in the federated learning process. Thanks for your attention.